Welcome to the Introduction to the Acceleration Stack for Intel Xeon CPU with FPGAs online training. My name is Carl. In this training, we will cover the acceleration stack for Intel Xeon CPU with FPGAs. We will cover the basic components of the acceleration stack, different design flows to use the FPGA as an accelerator that interacts with the acceleration stack, and talk about the features of the FPGA accelerator card. Here is the agenda for this presentation. We will start by talking about the basics of why Intel FPGAs are very useful as accelerators in the data center. We will then move on to talk about the different layers of the acceleration stack for Intel Xeon CPUs with FPGAs and how the different layers communicate. Then we will discuss the FPGA drivers and the Open Programmable Acceleration Engine, or OPAE, that are part of the acceleration stack that a host software program can use to utilize the capabilities of the FPGA. After that, we will talk about the two different accelerated development flows for the FPGA, the OpenCL development flow and the RTL development flow. Lastly, we will talk briefly about the capabilities of the Intel Programmable Acceleration Card. It's no secret that performance demands on data centers is ever increasing. Intel FPGAs can be used effectively in the data center to meet the compute demand for many reasons. FPGAs can be dynamically configured with a custom hardware circuit specifically for a particular workload, ensuring optimized performance for the given task. In addition to performance, because FPGA is custom hardware tailored for a specific purpose, this also results in efficient performance and improved performance per watt. Also, with workload optimized accelerators like Intel FPGAs, you end up with low latency, predictable performance as data is streamed through and processed by the FPGA. Finally, Intel offers developers an advantage when using Intel FPGAs by providing a common developer interface, tools, and IP, which makes it easier to leverage FPGAs. Overall, supercharging the Intel Xeon processor with Intel FPGA accelerators can reduce overall total cost of ownership and improve performance in a variety of workloads. Intel has invested in many tools and products that allows for FPGA acceleration to be enabled easily in the extended Intel architecture. In this ecosystem, software can easily manage FPGA acceleration, and Intel architecture virtual machines can take advantage of the FPGA accelerator through well-defined APIs and interfaces. Intel also provides many solutions for development. We provide turnkey board solutions, libraries to enable many end markets, various development flows from the traditional RTL to high-level software-centric methods to develop custom hardware for the FPGA. Intel has the tools and solution to enable developers in the Xeon plus FPGA ecosystem. Lastly, with Intel FPGAs, you will also have the choice in form factor. You may choose the discrete solution, where the FPGA sits on a PCIe card with its own off-chip memory, or you may choose the integrated solution, where the CPU and FPGA are in the same package, connected together by PCIe and the cache-coherent UPI connectors. Overall, we provide the tools and products that empower developers in the modern Xeon plus FPGA data center. Here we see the layers of the acceleration stack for Intel Xeon CPU with FPGAs. The acceleration stack is a robust collection of software, firmware, and tools designed and distributed by Intel to make it easier to develop and deploy Intel FPGAs for workload optimizations in the data center. The acceleration stack provides optimized and simplified hardware interface and software APIs, saving the developer time so they can focus on the unique value-added proposition of their solution. Code reuse is now possible with a common developer interface for Intel FPGA data center products. For even faster time to market, system-optimized reference libraries are provided for target vertical, making it possible to leverage Intel FPGAs to supercharge performance with little to no prior FPGA experience. For FPGA IP developers who need to create custom accelerator functions to run on Intel FPGAs, the acceleration stack provides the Intel FPGA SDK for OpenCL. OpenCL is an industry standard C-based programming language that allows users to abstract away the traditional hardware FPGA development flow and use a faster, higher-level software development flow. Traditional RTL development is also supported, allowing advanced developers to carefully craft and optimize the finest detail of their design. developers are free to choose whichever flow is most appropriate for their situation. The Intel Acceleration Stack for FPGAs simplifies performance increases in your application using Intel FPGA data center products. This diagram illustrates how the hardware and software interacts with each other in a possibly virtualized framework using the Acceleration Stack for Xeon CPU and FPGAs. Above the dotted line is the Xeon software layers. Users will develop applications that leverage the acceleration libraries that are written by the user or provided by Intel or third-party vendors. These accelerator library functions will then call the driver layer. The driver layer consists of the open programmable acceleration engine layer, provided by Intel, which provides low-level access to the FPGA accelerator and abstracts the lower-level PCIe and UPI drivers that are also provided by Intel. On the FPGA hardware side, the actual Accelerator Function Unit, or AFU, on the FPGA can be user-developed or Intel or third-party provided FPGA bit streams. It will plug into a standard slot available on the FPGA. On the FPGA, there is also the FPGA Interface Manager, which bridges the connection coming from the processor to the Accelerator Function Unit. This FPGA bit stream is provided by Intel for each board. As you can see, the Intel Acceleration Stack provides the pieces that allows user application to communicate to the Accelerator Function Unit with layers on both the software and hardware side. This slide shows a detailed look at the software stack in the virtualization framework. In this framework, the user focuses on the application and the acceleration function, showing green, while everything else is provided by the Intel developed software stack. So the user application and accelerator functions on the FPGA work seamlessly together since the framework is Intel developed and qualified with ecosystem partners. As part of the framework, you can see at the bottom is the Xeon CPU communicating with the FPGA. The hypervisor is at the bottom of the software layer in the virtualized framework. The operating system will sit on the top of that, and the FPGA drivers are above that. The OPAE, or Open Programmable Acceleration Engine, communicates with the FPGA driver, and the user application, or application library, calls the OPAE API. With this software stack, the application developer focuses on accelerating their core workloads and not worry about the infrastructure. On the FPGA, here are the components that enables communication to the Xeon CPU and the software stack. The FPGA interface includes an interface to the main processor, either PCIe as shown or UPI on multi-core package products. This is connected to the FPGA Interface Manager, or FIM, that handles the translation of commands and responses from the PCIe to and from the Accelerator Function Unit. Included in the FIM are protocol control, caches, address translation, and other logic to make this connection possible. The FIM is connected to the user-created Accelerator Function Unit via the Core Cache Interconnect Programmable, or CCIP interface, which defines the accelerator side of the interface. If you're designing the AFU using OpenCL, then you don't need to know how the details of the CCIP interface work, as that is abstracted away in the OpenCL flow. However, if you're designing your AFU using the RTL flow, then you will need to ensure your AFU conforms to the CCIP standards. The entire AFU is located on the FPGA in the partial reconfiguration region. This allows the FPGA hardware to reconfigure the AFU bitstream accelerator functionally. When using a discrete FPGA on a PCIe board, the AFU will also have access to external memory controllers, which are connected to off-chip memory, such as DDR4 memory. At the heart of the acceleration stack is the acceleration environment for Intel Xeon CPU and FPGAs. Here we see the CPU on the left and FPGA on the right. The goal is to allow user application running on the CPU to take advantage of the accelerator function on the FPGA, which can be created by the developer or provided by Intel or third-party vendors. A layer down, the acceleration environment has a software component, the Intel Acceleration Engine with OPAE technology, and an FPGA component, the FPGA Interface Manager. Together, these provide the common developer interface with simplified and optimized APIs and interfaces from Intel. This will abstract away and simplify the communication between the FPGA and the CPU, which is connected using PCIe or UPI in multi-chip packages. The FPGA itself may also implement high-speed interfaces that can stream data in and out of the FPGA. With this ecosystem, developers can build their own accelerator applications and accelerator functions directly on top of the acceleration environment and reuse that code on different Intel FPGA form factors in the data center. Or they can take advantage of the acceleration libraries for FPGAs to fast-track their performance and time to market using accelerator functions provided by Intel or third-party partners. The software interface to the FPGA driver is the Open Programmable Acceleration Engine, or OPAE. It is a collection of software components and APIs that simplify and streamline integration of programmable FPGA accelerators into software applications and environments. It consists of a set of drivers, user space libraries, and tools to discover, enumerate, query, access, manipulate, and reconfigure programmable accelerators. There are many advantages of using this technology. It is designed so you can use a common programming model across different FPGA platforms and form factors. The lightweight user library, libFPGA, has minimal overhead and latency. The OPAE ecosystem is open source with the API distributed on the BSD license, while the drivers are GPL licensed because the drivers are being upstreamed into the Linux kernel. The OPAE technology supports both virtual machines as well as bare metal OS platforms. The OPAE technology is also fully compatible with the AFU simulation environment, which allows you to simulate the interaction between the OPAE layer and the FPGA in an industry standard simulation tool even before the availability of the FPGA part. Lastly, OPAE comes with guides, utilities, and sample code. For more information and links to the source on GitHub, please visit 01.org/OPAE. Sitting underneath the OPAE layer is the FPGA driver. This slide shows the FPGA driver architecture. This is what's interacting with the FPGA. In a non-virtualized environment, the host interacts with the FPGA through just a physical function. In the virtualized environment, as shown in this diagram, the driver in SRIOV mode allows the host to use the physical function PF to access management functions, while a virtual machine uses a virtual function VF to access the AFU. The driver here is divided into three pieces: the FPGA management engine, or FME, part of the physical function, handle FPGA management tasks such as thermal and power management, reconfiguration, debugging, error reporting, etc. The AFU driver, which exposes a 256 kilobyte region as control registers, allow users to actually control and operate and share memory buffer with the AFU on the FPGA. Lastly, there are ports. Each port attaches to an AFU, and there may be multiple ports, so each port can be assigned to a different virtual machine. This slide summarizes the type of calls that the user can make using OPAE to manage and transfer data and execute the FPGA accelerator. The flow is fairly simple. You will first create FPGA properties, which is an opaque type which allows you to search for resources that suit your needs. You will call FPGA enumerate with FPGA properties, which will return a list of tokens that matches the FPGA resources you're looking for. With a token, which represents an FPGA resource, users can call FPGA open to acquire ownership of that resource, which will return a handle. With the handle, users can then perform numerous tasks such as reconfigure FPGA functionality, map and unmap register file of an accelerator into the virtual memory space of the calling process, prepare memory buffer to share between the calling process and the accelerator, transfer data to and from the device, control the accelerator, and others. Once the user is done with the AFU, FPGA close can be called to relinquish ownership of the FPGA resources. We will discuss details of each of these calls in a follow-on training, the RTL development training. Again, these APIs are only needed in a non-OpenCL environment. With OpenCL, the OpenCL host API library abstracts the OPAE calls. We've talked about how to access the FPGA accelerator from the user application software, but FPGAs are blank plates. So how can FPGA accelerator be created? Well, there are actually many paths to create the Accelerator Function Unit. The easiest is to externally source your FPGA accelerator IP. If you don't have FPGA IP development expertise, You can get the AFU bit stream from Intel reference designs, for example, or through a contract engagement to have an ecosystem partner develop specific accelerator functions for you. The acceleration stack for Xeon CPU and FPGAs also allows application developers to self-develop the FPGA IP. If you're already a seasoned FPGA developer, then you can use a traditional RTL-based approach to develop and optimize your FPGA IP in the Quartus Prime design software environment using RTL-based languages such as VHDL or Verilog. All you need to do is make sure your AFU IP conforms to the CCIP interface standards that we've talked about. If you're looking for a software-centric way to develop FPGA IP, the acceleration stack supports an OpenCL flow through the Intel FPGA SDK for OpenCL. In this scenario, Intel provides the OpenCL board support package, and all the user needs to do is to develop and optimize their OpenCL kernels for the FPGA in the C-based environment. This approach makes FPGA development easy and accessible to parallel software developers. The RTL and OpenCL flows for the acceleration stack are described in more detail here. The RTL programming tool flow is shown on the left. FPGA IP development uses the same Intel Quartus Prime tool as traditional FPGA development. On the software side, Intel Acceleration Engine with OPAE technology from Intel is used for software programming of the CPU. To facilitate functional verification, Intel provides the AFU Simulation Environment, or ASE, which is the environment which lets you functionally simulate the accelerator function RTL with the same application code you will run on the actual FPGA hardware without the FPGA being present. This flow allows the utmost customization and utilization of the FPGA. The OpenCL programming tool flow is shown on the right. OpenCL is an industry-standard C-based programming language. It allows users to abstract away traditional hardware FPGA development flow for faster and higher-level development. Intel will provide the OpenCL board support package, which allows the Intel FPGA SDK for OpenCL to automatically construct kernel compute unit with the CCIP AFU interface. The SDK, with the help of traditional software compiler, will also generate the appropriate software code that is run on the CPU. Users will need to know the OpenCL host API and not the OPAE interface. Before creating the actual bitstream, the OpenCL flow allows users to emulate the OpenCL C kernel on x86 machines to easily perform functional debug. This flow is more productive of the two. With the OpenCL flow, the usage is no different from traditional OpenCL flow, and the user application looks like a standard OpenCL FPGA application. You will still develop and debug your application and accelerator kernels in a C-based environment using the Intel FPGA SDK for OpenCL. The only difference is that the OpenCL layer sits on top of the accelerator stack, so it's abstracted away from the user. The OPAE software layer in the OpenCL flow is included as part of the host runtime, so users does not need to interact with OPAE software directly. They use OpenCL host API, same as all OpenCL applications. The OpenCL BSP FPGA interface hardware is included as part of the FPGA interface manager, and it will handle translations of the CCIP protocol to the Avalon interface used by Intel FPGA OpenCL kernels. Again, this part is abstracted away from the user, and the user just needs to write regular C-based OpenCL kernels. To debug and optimize, all debug and profiling capabilities of the Intel FPGA SDK for OpenCL, which includes emulation kernels, load and store profiling capabilities, are still supported in the accelerator stack environment. For more information about how to use OpenCL to develop accelerators on the FPGA, please visit the Intel FPGA customer training webpage. If the accelerator application developer wants to have absolute control over the FPGA IP and also has FPGA development expertise, then the RTL AFU development flow is available using standard FPGA development tools. In this flow, the application user focuses on the development of the AFU using a behavior language such as VHDL or Verilog in the Quartus environment. The user will have to ensure the RTL IP supports the Core Cache Interconnect standard, which interfaces the AFU with the acceleration stack through the on-chip interconnect, which is part of the FPGA interface manager. The CCIP interface is a memory mapped interface that supports simple read and write requests and responses. The interface uses physical address and uses a tag to match responses to requests, so no order is guaranteed. This type of minimal requirement interface actually satisfies majority of algorithms suitable for the FPGA. You can, for example, double buffer kernels that read from and write to different buffers, and it can also very importantly support streaming kernels that read from one memory map FIFO and write to another. With the RTL flow, it's important to take advantage of the AFU simulation environment, or ASC. This simulation feature offers application developers the ability to seamlessly port both the software and RTL code from the simulation environment to real hardware without modifying either source. The simulation environment supports both the OPAE software layer on the software side and the CCIP protocol on the AFU side. With ASC, users can verify OPAE software together with AFU RTL without the availability of FPGA hardware. The software application simply loads the ASC library, which supports OPAE, and automatically connects to RTL simulation using the System Verilog DPI feature. For execution on hardware, the application developer simply needs to change the linked library to the runtime library while the RTL is compiled by Quartus into FPGA bit streams using the same source used in the simulation. The FPGA hardware that supports the acceleration stack and the development flow is here. The Intel Programmable Accelerator card with Intel Aria 10GX FPGA is the first platform to support the acceleration stack for Intel Xeon CPU with FPGAs. This is a versatile Intel-qualified low-power FPGA PCIe acceleration card that can be used for both loci acceleration workloads or inline acceleration. This board supports inline acceleration with network connectivity. The ability to support enables broader FPGA adoption in the data center. For more information and detailed specs about the Intel Programmable Acceleration card with Intel Aria 10GX FPGA, follow the hyperlink at the bottom of this slide. This concludes the training. To summarize, the acceleration stack for Intel Xeon CPU with FPGAs is a robust collection of software, firmware, and tools intended to make it easier to develop and deploy Intel FPGAs for workload optimizations in the data center. We've discussed the various layers of acceleration stack and how they work together, the API to interact with the FPGA, the various development flows to develop an accelerator function unit on the FPGA, including both the RTL and OpenCL development flows. For more information on the acceleration stack and available platforms, please visit the Intel FPGA Acceleration Hub. As a follow-on training, see the RTL development and acceleration with the Acceleration Stack online training. If you would like to learn more about the OpenCL flow, please visit Intel FPGA OpenCL training web pages. Lastly, please consult the various quick start guides and develop guides associated with Acceleration Stack for more information. Thank you very much for attending this training, and best of luck with all of your designs.